consider the omega to be set of natural numbers. Okay? So if omega is set of natural numbers, then what will be in B of omega? Okay? What will be in B of omega? So F are maps from omega
F1, F2, F3 वो सुप्रीमम of all those F1, F2, F3 सबके ऊपर कंप्यूट करेंगे.
These are going to be sequences actually.
Sequence.
These are going to be sequences.
Fn.
Okay, the B of omega is going to
Supremum
comprise
of
of
sequence.
sequences in K. Okay? Where I belongs to N. And what property that these sequences must have?
Increasing.
So when I say that a sequence is bounded, okay, so if we have a function, so it's like, okay, so like a sequence is a function. So we say that a function is bounded if the magnitude of function at all values is smaller than or equal to C.
Series.
But,
Series.
but what do you think that when a sequence is going to be bounded, you don't need a series to for the boundedness of the sequence. The sequence is bounded if each term is bounded by a number. Okay. Sequence is bounded if each term in the sequence is bounded by a number. Okay. So, okay. So here's the thing. I'm saying, just try to figure it out for yourself. I'm saying that it's a collection of such a sequences for which the supremum of xi's where I belongs to n is finite. Is finite. यार एक काम तो करो बच्चे, ये जो नीचे शोर चल रहे से कोई बंद करो ये क्लास चल रही है. ठीक है? Okay. So, is it making sense? Why does this make sense? Because each of the term of this sequence can be estimated by the supremum. This is true that everything is fine. Okay. And what should be the meaning of then the infinity norm? In other words, now my x is no more going to be a function, or my f is no more going to be a function, but it's going to be a sequence actually. So it's going to be something like this, x1, x2, and so on and so forth, where each of these xi's are from K. Okay? So what should be the meaning of x of infinity? What should be the meaning of this?
Supremum of I belongs to n of x.
Supremum of each term, absolute of each term
What?
of the sequence.
Give me the expression.
Supremum of absolute of xi.
Supremum of x. Okay. So the supremum of roughly x1, x2, absolute of x3, so on and so forth. This must be the infinity norm. Okay? Is it making sense?
जो कैलीग्राफिक भी है उसके लिए डिफाइन किया ना सीक्वेंसेस के लिए उसमें थोड़ा जो आपने वो कंडीशन सुप्रीम शुड इसका मतलब सर जब हमने कैलीग्राफिक इस पर्टिकुलर केस लिए नहीं सर वो नीचे जो आपने
ये
सर ये जो डिफाइन किया आपने कैलीग्राफिक बी फॉर दैट एन ये मतलब समझ नहीं आ रहा है।
देखो ना बेटा, so if I have an f from n
टू के
into k,
सही
then I'll have f of n actually for each n,
ओके
and I'm giving it a name xn,
ओके
xi, and I keep xi,
सही
and then इनसे बनने वाला जो sequence होगा, just like x1, x2, so on and so forth, so I'm calling it basically x, ठीक है, इससे मैं बना रहा हूँ complex, so that's what I'm doing, ठीक है. So this is what the definition of xi is. Okay. Okay, एक और चीज, the last thing that I would like to tell. This space is particularly called L infinity space. So we call it L infinity. Okay? So L infinity is the sequence which will be real, which will be, complex sequences such that the supremum of xi is finite, and you define norm on this space. Okay. Another example. Okay. Another example. So this L infinity space must be kept in mind, because this is an important example. So what the examples that we are at the moment doing are elementary, and they all are important actually. And obviously, if you proved that this space is a normed space, then this is just a corollary of it. So if this is true for any omega,
then
this must be true.
omega is equal to
So you don't need to do it separately. So,
इस मेजर प्रोडक्ट को हमने यूज नहीं किया।
we haven't used it, and probably we can't use it here. If you try to define in a product out of it, probably it will be difficult.
Yes.
Okay, so here's the next space which I am defining, L1. Okay, L1. So L1 space is the space of the sequences, okay, that R belongs to N, such that all of these xi's are in K, and this sequence is absolutely convergent. So it's a collection of those sequences which are, what do you call this, sequences for which the corresponding series is absolutely convergent. Okay. And you call such sequences as absolutely summable sequences. We finally going to generalize it afterwards, not now. Okay, we're going to generalize it up to P basically, so LP. So it's going to be true for any of these, but we're gradually doing it. What should be the meaning of norm on this? Okay, whatever the meaning of norm should be, so give it a 1. So since it is 1, so I'm going to call it basically what? The one norm. So what do you think, what should be the definition of?
Summation of x.
Exactly. So the norm, the size of this should be the summation I equal to 1 to infinity xi. Okay? So this series, actually, if this series converges, you're going to call that as the size of basically x. Okay? And task is what? Your task is to do the same. Verify it, it's a normed space, it's a vector space roughly. So for vector space, you just only care for addition and scalar multiplication, because the rest of things are pretty much straightforward actually. But for the normed spaces, okay, the proof of norm, try to do it fully. Okay, this is important. All right. Now, this example is an interesting example because this is the first example for which the parallelogram law is not true. So, if the parallelogram law is not true, that means that you can't use this norm to define inner product basically, so on and so forth. Or you can't.
This inner product
Space is not an inner product space actually. It's not an inner product space. Okay. You can't define an inner product on this space unless you do something crazy. Is it making sense? Okay. So, what is the normed space essentially? So, a space on which you have a norm, a fashion to compute the sizes of element, and once you have that, you have to do, you have a normed space. Okay, so next thing is that I would like to take this analysis to a new level. Okay, I would like to create some more, what you call crazier examples of vector spaces and the normed spaces. And the upcoming section is going to be very important. All of these basic things are important. So the next discussion is going to be on bounded linear maps actually. Okay? Bounded linear maps, and we're going to. So I hope that I don't need to tell you that what is the meaning of a linear map between two vector spaces. So it's like a T is a map, linear map from E to F. Here F are some vector spaces. If it lays nicely with addition, okay, and scalar multiplication, okay. So if this is true, that T is what we call a linear map. We have so if we take so if E is in a product space over K, the field K, then any linear map which is a map from E into its field K, we call it as an operator. We're going to call it as an operator, and sometimes also it is also called functional. But functional has more than linearity, should have a boundedness as well. Okay? Is it making sense? Okay.
ये मैप जो है लिनियर है और ई से फील्ड तक है.
Yes.
तो वहाँ पर सर वो डेफिनेशन किस तरह होगी हमारी लीनियर इमेज वाली?
E is in a product space, hence a vector space. K is in a product space, hence a vector space. So what's it?
सर उसमें जो डेफिनेशन है टी ऑफ सम के ऊपर अप्लाई करते हैं तो वो भी एलिमेंट कोई मतलब वेक्टर स्पेस का है और वहाँ पर भी वेक्टर स्पेस में उसके ऊपर तो यहाँ पर हम
So this is an element in vector space F, and these two also are elements in vector space F.
but in
This addition is in F actually, while this addition is in E. Okay. After doing a course on linear algebra, we must be I slightly don't agree with notation that he is using for the book. If calling this as operator, why we use word operator usually in higher sciences if you have a linear map from E into itself actually, not E into K. So for E into K we use terminology functional, but strangely this guy is using the notion of linear operator or operator and for the maps which is E to K, which I slightly don't agree with. Okay. Can we, okay, can I, so can I add two linear maps? In other words, let's take two linear maps, okay, which are, from, for example, E to F. Question, can I define T plus, so it's like a T plus S actually, where T and S are both linear maps. So what do you think, what would be the sum of these linear maps?
Also linear.
So operated onto, for example, F, which is F is an element in E. So it must be pointwise addition. F plus okay.
Should it must be, or we have defined it this way?
We have defined it this way. We have defined it this way. We can add it in.
वहाँ पर जो एडिशन है वो की वाली
And then obviously, so imagine that if I have a set which comprises of all linear maps from E to F, okay, so can I turn that set into a vector space? Okay, so it's like if I have a set of all linear maps from E to F, question is, I don't want to use a notation actually now because okay, I'm leaving it for some moments. Okay, so I have two maps, okay, which are linear from E to F, and I'm defining a new linear map, okay, out of these two maps, which is this basically. When this map is going to be well defined, obviously when T plus S is it's linear itself. Okay, so you need to check that whether the sum of two linear maps is a linear map or not. And similarly, if I have lambda T, okay, operated onto F, what should be its definition? So it should be lambda times TF actually. Okay. So this TF is basically composition. So not composition, but T operated onto F. So T of F actually. So this is what that we're going to use. So again, this will be the question that is this linear? Is this linear? Okay. Is this linear? The answer is yes actually. So in both cases, we can show that the answer is yes, but you must verify. Okay? So using this, I can say that, okay, if I have set of all maps, okay, which is,
T is from E to
T is a map from E to F, and it's linear.
so F
So
or field K.
F. In general, F.
Where F is the field.
Yeah.
Field.
When F is a field, then it has a particular, name actually. Okay, which probably you should know as well.
Sir,
Sir,
F
Okay, let's at the moment consider this. Okay, so I'm saying that it's a collection of all linear maps between two vector spaces.
okay.
Okay. Now I can turn this with these addition and multiplication. I can turn this into a vector space. Okay, I can turn it into a vector space.
so what would be 0?
Huh?
0 element.
Yeah,
Zero element is going to be the zero
Zero is
map.
a linear map.
Zero map is a linear transformation.
0 by K.
Zero of T. Zero of F.
0 by is what?
Linear map.
Zero of F. Zero of T equal to zero.
Okay,
Zero of F is zero.
and it's linear.
Define curve.
Anyway, so it's a vector space. Okay, it's a vector space. And if F is K, this vector space has a particular name.
Functional.
Functional space.
No. Okay, so it's like it's going to be the space of functionals, but this has a particular name. And that name is, you heard of that? I think it's called the dual. So who you call it, it's okay, if F is K, then this space is called E star. It's a dual of E actually. Have you heard of dual?
Yes.
Anyway. So here's a question actually. So if we have this new vector space, okay, on which we have this addition and scalar multiplication, can we turn it into a normed space? In other words, can I define a norm of a linear operator? Okay. So here's the question. If I have to define the norm of a linear operator, what should be its definition? Or the size of a linear operator?
Make it a matrix. Every linear transformation gives the matrix. Linear transformation gives the matrix.
No, it's true infinite dimension. It's true infinite dimension. Okay, maybe you have a way to give it a name in finite dimension, but E is in abstract space. So what should be done actually? The straight answer is no actually. Okay? It's not the case. There are operators. We're going to see some examples, for which you can't have a norm. For example, I can't compute the size of differentiation operator, this guy, roughly. So
are there any operators whose norm can be computed?
yes. So the first thing is that if I say you that okay, what would be your way or maybe your trick to define the norm of the linear operator? So if you are allowed to use anything,
Discrete numbers. 0 and 1.
0, 1.
A discrete norm means
So one candidate could be, just think about it. One candidate could be what?
Every transformation gives
one digit.
every transformation gives the matrix and take the maybe.
Field की खबर है. Field की suppose कर रहा है.
R suppose क्या होगा?
Okay, you may also assume, okay, let's,
So is it going to our K?
you may also assume a structure on E and F that, okay, they are normed spaces. Okay, roughly.
So
अच्छा.
So you have norms on E and F. Okay.
Does
Does it give you any hint?
F is equals to K in the complex.
सर वहाँ पे ही दे दे वो उसके बाद.
F पे जो norm है उससे क्या करें? What should I do with the norm of F?
जो हमारी इमेज आ रही है
Good. It's a good heading. So let's take the norm of TF with respect to F actually. But here's the trouble. There are lots of F's in F actually. So what should I do? So there are lots of F's in capital F. So what should I do? Sum kar. Okay. So let's think. So take the sum actually. Sum over all F's which are in F. Here is the question. Does this series converge? Okay, then another choice could be take the supremum of TF. Here's a question. Does supremum exist? Why the supremum would not exist? So just think about it. So I have a collection of TFs such that F is from F actually. So why the supremum for this set doesn't exist?
F from E sir.
F from
F आया
no F from.
TF हाँ क्या TF वाले में सही
Okay. So why supremum of this set must exist or shouldn't exist? When supremum exists, if the so that's a set of real number undoubtedly. Okay. If it is bounded actually. So do we know that this set is bounded? We don't know that. How can I turn this set into a bounded set? What should I assume? We have just did it some moments before.
Every function is bounded.
F is bounded.
So when this set is going to be bounded?
Every TF is bounded.
If T is bounded.
Every TF is bounded.
Exactly. If every T, so it's like if you assume that these magnitudes are bounded, okay, so if you can find a number which is bigger than all of these TF, we are done. But if we are saying that the magnitude of TF is smaller than or equal to some number for every F, what does it tell you about T?
T is a bounded function.
T is bounded.
So you need boundedness of T actually. Then you can define the norm. So you can't define with the linearity. So the linearity is not enough. So what we just tried to figure out, okay, is that, you know, if you assume your T additionally linear and bounded, then you can define the norm on it. Okay? Is it making sense? So see, I could have written this definition, you know, without telling you that why the definition is like that, but now you can see that. Here's the definition. Here's the definition that imagine I have a normed space E with norm E